Question number 4. This barbell is spinning in space with some string holding it at some distance d naught. When a motor at the center pulls it in to 1/3 its original distance, what happens? When you see something like this, the first thing you should say is there's no external torques, there's no hand coming in. So the one thing I know for sure is that angular momentum is conserved. Okay, and so you can go and answer that question right away. Is L goes to 1 times L naught. There's no change. You want to talk about energy? No. Energy is a tricky partner because an internal motor can convert electrical energy to mechanical energy. Friction can turn mechanical energy into heat, like if there's a collision or if there's something sliding against itself. But you know, momentum and angular momentum are always going to be there for you. So then you look, alright, the moment of inertia, mr squared. So we know the moment of inertia must go down by a factor of 9. How about omega? Well, L, angular momentum, is equal to I times omega. So if this gets smaller by a factor of 9, omega must go up by a factor of 9. How about the kinetic energy? Well, that's equal to 1/2 I omega squared. If omega goes up by a factor of 9 and this goes down by a factor of 9, I square it. So this must go up by a factor of 9. But I don't like this formula. The one I like much better is 1/2 L squared over I. Check and make sure that's the same. Because I know this is conserved. So this doesn't change. Therefore, if I goes down by a factor of 9, the kinetic energy must go up by a factor of 9. Okay, now the one that all of you got wrong, and the grader graded it wrong on your paper too, so pay attention, is what happens to the tension in the string. Everyone wrote, oh, tension doesn't depend on length. Yes, but what does tension depend on? It depends on how hard you're pulling on the string. Why is there tension? There's tension because we need a force to pull these objects into a circular path or else they keep going straight. So that must be equal to mass times centripetal acceleration. So we ask ourselves, what happens to the centripetal acceleration that's necessary to pull these guys in as the radius drops and omega goes up? And we recognize that's mv squared over r. I don't really like that. I like m omega squared r better because I can see this goes down by a factor of 3, but this goes down by a factor of 3, but this goes up by a factor of 9, and it's squared. So this is 81, and this is 1/3. So it goes up by a factor of 27. Which makes me realize it's also wrong on your solutions. I had the wrong solution on your solution. So you better pay attention. In any case, I don't like the way this is written either, because all of these are changing. I want to put this in terms of L. So how about if instead of omega squared, we expressed omega as angular momentum divided by I. So then we have m L squared over I squared times R. And so I is equal to mr squared. So making this substitution, we have m squared r to the 4th in the denominator. This cancels with one of these, this cancels with one of these, and we have L squared over mr cubed. And so this way we can express the tension in the string in terms of something that doesn't change, and see that when the radius gets smaller by a factor of 3, the tension is going to go up by a factor of 3 cubed, or 27. Now that we've expressed this tension on the string in terms of something we know, we can find out where that kinetic energy came from. Was it really due to the work of that motor pulling the two masses closer together? Because the kinetic energy is L squared over 2I, because I drops by a factor of 9, the kinetic energy jumps by a factor of 9. So the final kinetic energy is 9 times the original kinetic energy. And we wonder then, where does that 8 times the original kinetic energy come from? And so we say, alright, it's the work. Work is force times distance. But because the tension changes as the radius gets smaller, we need to make it an integral. And so it's tension.dr, and I put the tension in terms of something that's a constant. Oh, it's a constant, so we don't have to have an L naught, because final angular momentum is equal to initial angular momentum. So we substitute that in. The key factor is r cubed is in the denominator, and these are constants, so they come out of the integral, and we just have to integrate r to the negative 3, which is negative 1/2 r to the negative 2, and we evaluate it at its limits, which is just 9 over r squared minus 1 over r squared is 8 over r squared. And substituting in, we find, sure enough, the work done by that motor pulling them in is equal to 8 times the original kinetic energy, which accounts for the extra energy that we got in the process. Alright, so there's a minus sign here. Where is the mistake I made? The mistake I made was that I defined this as the positive r direction because I integrated from here to here. So that means this is positive r, but tension is in this direction. And so really I should have had a negative here, and this would have all worked out just fine.